Hi friends and welcome to my new video. I have created this video for developers who want to build a chatbot and don't know where to start. The goal is not to teach specific APIs or frameworks, but to give you a mental model that actually survives contact with reality. By the end, you should understand what components are involved, how they fit together, and where dev teams usually go wrong. Great, let's begin. The most important mindset shift is that a chatbot is not an LLM. The LLM is a probabilistic component that produces likely outputs, not guaranteed ones. Everything around it exists to constrain, guide, and control that behavior through deterministic code. When chatbots fail in production, it's rarely because the model was weak. It's usually because the surrounding system failed to properly wrap probabilistic behavior with deterministic logic. I have prepared this mental diagram to make it easier for you to understand the flow. At a high level, every chatbot follows the same flow. A user interacts with a UI, which calls an orchestration layer. Before any model is involved, documents are prepared through pre-processing, chunking, and embedding, and stored in a vector database. Typically, this is done as another parallel process. At runtime, retrieval selects relevant chunks, a prompt is assembled with rules and context, and only then is the LLM called to reason and generate a response. Finally, the output is checked before being returned. It's important to keep in mind that most of a chatbot's quality is determined before the LLM ever runs. The model does not fix bad data or poor pre-processing, it only reasons over the context it is given. The UI is deliberately simple. In practice, what it really does is make API calls to the chatbot backend. It takes the user's input, sends it as a prompt to the chatbot engine, and then displays the response that comes back. That's it. There is no intelligence here, no AI decisions, and no business logic. Keeping the UI thin makes the system easier to reason about, easier to replace, and much safer to evolve over time. The orchestration layer is the real brain of the system. This is where decisions are made about retrieval, permissions, prompt structure, and model usage. While you can build this logic yourself, it is strongly recommended to use orchestration frameworks like LangChain, LangGraph, Semantic Kernel, or other popular frameworks. These frameworks help structure complex flows, make behavior explicit, and reduce the risk of fragile ad hoc implementations. They accelerate development, but they do not replace architectural thinking. Cloud models are usually the fastest way to start and tend to offer the best raw model quality, which is why many teams begin with providers like OpenAI, Azure OpenAI, Anthropic, or Google. On-prem models, such as Llama or Mistral-based variants, give you more control over data locality and cost predictability, but they come with operational overhead. The important point is that neither approach is inherently superior. This is an architectural trade-off based on data sensitivity, cost, latency, and operational maturity, not a belief system. Hybrid architectures are very common, especially when data sensitivity or regulatory requirements are involved. However, many teams also choose full cloud setups for reasons of simplicity, speed, and lower operational burden. In those cases, both retrieval and the LLM run in the cloud. What matters is not where components run, but that retrieval happens before inference and that data access and context boundaries are explicitly designed and understood. Embeddings are how we translate language into something machines can compare. They convert text into numbers that represent meaning so that similar concepts end up close to each other in vector space. This allows the system to perform semantic search instead of relying on keywords. When a user asks a question, we embed the question and look for nearby vectors that represent relevant content. An important detail is that embeddings are usually generated ahead of time and reused at runtime. They are part of the data preparation pipeline, not something the model creates on the fly. There are many good embedding models available today, both proprietary and open source. What matters most is consistency and alignment with your data, because embeddings are a foundational building block for retrieval augmented generation. This example shows what embeddings are actually capturing: intent and meaning. The first two questions use different words, but they are clearly about the same thing: submitting expenses. Their embeddings end up close together. The third question is about time off, which is a different topic entirely, so its embedding is far away. This is why embeddings enable semantic retrieval. We're no longer matching keywords like expense or report. We're matching meaning. Importantly, these embeddings are generated ahead of time and stored. At runtime, we only embed the user's question and perform a similarity search. The model itself never searches documents, it only reasons over what retrieval gives it. Vector databases are optimized for similarity search over embeddings. On-prem, teams often use options like PostgreSQL with pgvector, Qdrant, Milvus, or Weaviate. In the cloud, managed services such as Azure AI Search, Pinecone, or hosted vector databases are common choices. In practice, the specific database matters far less than how you chunk, embed, and retrieve your data. Poor chunking will hurt answer quality long before the choice of vector database does. In a RAG setup, the LLM is primarily used for its natural language capabilities, such as understanding the question, reasoning over the provided context, and generating a coherent response. It is not used as a search engine, and it does not fetch data by itself. All data access and retrieval happen outside the model. The model's role is deliberately constrained, which is exactly what makes RAG systems more predictable, controllable, and trustworthy. Efficient chunking is only possible if the underlying data is properly pre-processed and structured in a way that can be meaningfully split. Messy documents, broken layouts, mixed semantics, or raw exports will inevitably produce poor chunks, no matter how strong the model is. This is why chunking cannot be treated as an afterthought or something you fix later with better AI. It is a data and engineering problem that directly determines retrieval quality and, by extension, answer quality. Grounding is not achieved automatically by using RAG. One of the most important tools for grounding is the system prompt. System prompts define the role of the model, the rules it must follow, and the boundaries of acceptable behavior. By clearly instructing the model to rely only on retrieved content, to refuse when information is missing, and to avoid speculation, you dramatically reduce hallucinations. In practice, good grounding is the result of disciplined system prompts combined with controlled retrieval, not model choice. This is a simple example of how grounding is enforced in practice. The system prompt defines the role of the model, its boundaries, and the rules it must follow. Notice what's happening here. We explicitly tell the model to rely only on retrieved content, to avoid guessing, and to refuse when information is missing. This turns hallucinations from a model problem into a system-controlled behavior. The important point is that grounding does not happen automatically just because you use RAG. It happens because the orchestration layer combines retrieval with strong system prompts that clearly constrain what the model is allowed to do. In other words, grounding is not about making the model smarter. It's about making the system more disciplined. Guardrails protect both users and systems, and they operate at multiple layers. Some guardrails are implemented by you, such as input validation, access control, and prompt constraints. Others can be provided by cloud platforms, for example, built-in content filtering, safety classifiers, and policy enforcement offered by managed LLM services. These cloud offerings can significantly reduce effort, but they should be seen as complementary, not a replacement for architectural controls. Safety is not something you bolt on at the end. It emerges from deliberate design choices across the system. Beyond the core chatbot flow, You almost always need a database to store session data and interaction logs. This includes conversation history, user context, and metadata about requests and responses. Persisting this data enables conversational continuity, helps with debugging and monitoring, and is often required for audit and compliance purposes. Importantly, this database is part of the deterministic system around the model and should be designed with clear retention, access, and privacy rules. So, based on all we have discussed by now, a realistic starting path should be concrete. You typically begin with a simple UI that calls an LLM through an API just to establish the basic interaction loop. Next, you introduce a proper orchestration layer so prompts, model calls, and behavior are controlled. Once that foundation is stable, you add RAG by introducing embeddings, a vector database, and a retrieval logic. After that, you can extend the system with tools, integrations, and stronger guardrails. Throughout this evolution, security and access control should already be present, and they are progressively hardened as the system moves closer to production. I have prepared this pseudocode to bring the mental model together into a single, concrete flow to make it easier for developers to understand it. Every request starts with validation and authorization before any AI is involved. The orchestration layer then decides whether retrieval is needed and, if so, pulls relevant context from the vector database. That context is combined with system rules and the user input to form a deterministic prompt. Only at that point we run model inference. The LLM is just one step in the pipeline, not the system itself. After inference, the output is grounded and checked, and the final response is produced. The interaction is then stored, often asynchronously, for continuity, monitoring, and auditing. The key takeaway is that reliability comes from the surrounding code, not from the model. The LLM reasons over the context it is given, but the system decides what that context is and how the result is handled. Most teams struggle not because the technology is immature, but because they solve the wrong problems first. A very common mistake is focusing on model choice or fine-tuning before the retrieval pipeline and data quality are in place. Another frequent issue is starting from tools instead of architecture, trying frameworks, libraries, or platforms without a clear understanding of how the system should behave end-to-end. Teams also tend to overestimate how much the model itself matters, while underestimating pre-processing, chunking, and retrieval quality. Finally, many systems fail because the UI is treated as the system rather than as a thin client on top of a well-defined backend. These are not AI mistakes. They are classic software design mistakes that simply become visible faster when LLMs are involved. If there's one thing to take away from this presentation, it's this. Building a chatbot is not about chasing models or tools. It's about understanding the flow and orchestrating the right components around a probabilistic core. When you get the architecture right, data preparation, retrieval, orchestration, grounding, and guardrails, tools become replaceable details. Models will change, frameworks will evolve, but a solid mental model will continue to serve you. Focus on building systems, not demos. If you do that, your chatbots will scale more reliably, behave more predictably, and remain useful long after today's hype cycle has moved on. Thank you for watching this video. I hope you found the subject as exciting and thought-provoking as I did. If you'd like more insights on AI, data, digital transformation, and other tech trends, be sure to subscribe to my YouTube channel. Take care, and I'll see you next time.